So yeah, bring on Kusuma and Dinakar, and we are going to say goodbye to Shai, and yeah, reach out to each other, because it looks like there's so much collaboration that you three can actually do.
Scale creates bugs, and we can feed off each other.
Save us from Kubernetes of some of the issues there of losing more Kubernetes clusters than I've had warm meals. Okay, thanks, Shai. Over to you, Dinakar and Kusuma, which you've got some incredible session to show us. I had to Google exactly what Bayesian scaling of your cluster is, though, and I felt a little bit like my Google search history was going to be confused of Master, but it was an incredible topic. And with Shai's also topic on there, it is a great opportunity to look at Kubernetes running on Azure also, and to do that. So over to you, Dinakar and Kusuma, and I look forward to your talk. Cheers, Shai.
Thank you, Rory, and definitely we'll reach out to Shai for the tool that he just mentioned. So hello, everyone. I'm Dinakar, and also have Kusuma Chalasani here with me. We both work at Red Hat and look into how Java can run better in Kubernetes, and that is what we'll be talking about today. So imagine that you're an SRE and you've been given this problem to be solved. You have a complex polyglot application, such as an airline booking system that is deployed onto a Kubernetes cluster. As you can see, it has many microservices, a couple of databases. Each of the microservices written in a different language and framework. The user is now, let's say, having a slow response time while doing a flight booking. Now it is the SRE or the IT admin's job to try and make the user experience better. So if you're an SRE, you know that every runtime has many tunables. Java, for example, has maybe even 100 of them. But you also know that you're never supposed to touch them. Right? Why? Because who knows what kind of an impact it has. And it has all these dependencies on other tunables. And there are just too many of them for you to manually test and figure out. And of course, now that we are running it in containers, nobody knows what happens inside of a container, right? So guess what? Most of the time, SRE is limited to tuning the app itself, or just limiting themselves to tuning the CPU and memory resources. By tuning, I mean just double the resources every time there is a problem, which is pretty much what happens with most of the SREs. So it is difficult to be an SRE, let's face it, right? You have the users bugging you for better response times. Finance wants you to cut costs always. And you have developers giving you a ton of options that you cannot use. So, well, don't worry, folks. We've got you covered. So Kruize Autotune is a tool that automates the entire process and provides a recommendation that best suits your performance needs. It's also an open source project. We are from Red Hat Frall, and I encourage you to check out our GitHub repo. So Rory mentioned about Bayesian optimization. So what exactly is Bayesian optimization, and how does it figure out here? So Bayesian optimization is a black box optimization algorithm where you have an objective function on the y-axis. That could be something like I want a better response time, or give me better throughput, or lower the cost, or even better, a mix of all of them. And on the x-axis, you have all your tunables. And so together, all of this is called as the search space. So for every point on the x-axis, which corresponds to a specific configuration, we find the result. So we actually run with the configuration, find the result. How does it do? How does your application do with that particular configuration? Find the result and plot it on the graph. So Bayesian learns from this result and gives you the next query point, right? So here the purple line is the ground truth, and the red points are the query points that is being given to you by the Bayesian algorithm. So it gives you a query point which corresponds to a trial configuration. You try that out, and then you plot the result. And then Bayesian gets better and better at predicting the next trial point. So that, let's say, for example, that you want to maximize your objective function. So that's to find the global maximum here. And so eventually, Bayesian gets to the global maximum. So that's the theory behind this. It's a very quick summary, essentially. So let's now look at how are we feeding this into the Autotune architecture. So the first step here is that the SRE encapsulates all of the performance requirements into an objective function, which is an algebraic expression such as lower my response time, but also keep the cost low, and so on and so forth. So that's the objective function here in the SLO. And this is, of course, something that needs to be either maximized or minimized. And each of the variables within the objective function is now specified as a Prometheus query, and this whole SLO applies to a particular deployment in Kubernetes, which is mentioned by the selector here. So if you apply this to the cluster which is running Autotune, the Autotune operator picks up this and then talks to the dependency analyzer module here, which peeks into your application through Prometheus. So it's not directly talking to your application, it's just talking to Prometheus and figures out the layers of your application. So for example, it can, your application can have Java and Quarkus or Spring Boot, or it can be a Node.js application or a Python application. And it can have many variants of Java. Like, for example, you can have a Hotspot or OpenJ9 and so on and so forth. So it tries to figure out all the layers of your application. And then we have a bunch of tuning sets, a library of tuning sets for each layer. So Java has a bunch of tunables, Node.js and Golang and so on. And so we match the two of them together and create the search space, as I mentioned. And then we feed this to the HPO, the hyperparameter optimization service that's running here. And you can also specify the algorithm that you want to use. So there are multiple variants of the hyperparameter optimization. We by default use the TP, the tree parson estimator, a tree structure parson estimator algorithm, which then gives us the trial configuration, as I mentioned. So we take the trial configuration, and the experiment manager module here deploys that to the Kubernetes cluster, and then monitors that particular configuration come up and looks at how does it do when load is applied to that. So that is captured, the metrics are captured, and the summarized results are then sent back to the HPO, so the hyperparameter optimization service. It says, okay, so now I've got the result of the first trial, and so on. So now this loop continues, and then we do a bunch of trials, and then at the end of that, we get what is essentially the global maximum or the minimum that I mentioned. And so that goes out to the user as a config recommendation. So now just let's take a look at how this works in practice. So I have here a Minikube cluster running on my laptop. As you can see here, it has a benchmark, the Tech Empower Quarkus Rest Easy Hibernate benchmark, as well as Autotune running in the cluster. I also have Prometheus and Grafana in the cluster. And so now I'm going to apply YAML here, Autotune YAML, which says, the objective function here is to minimize response time. And response time here is nothing but request sum divided by request count. Request sum is the following query, and request count is this particular Prometheus query. So I'm going to now just apply this here, and you can see that this starts to restart this application with multiple configs. And now we can take a look at what's going on here. So if I okay. So bring this here. So you can see that you can see the tunables that it has found. So let's take a look at the stack layers first. So here, we have this running, and you see that this is the experiment that is running. These are the layers that it found in this particular application, the Tech Empower benchmark. It has Hotspot container and quarkus, and then we have tunables, which are mentioned here for each of these layers. So we have CPU and memory as part of the container layer. I just have currently just one for Hotspot, and actually a few of them for Hotspot, and then a bunch of stuff for quarkus layer as well. And the thing to note here is that I'm also monitoring the heap space as we are running this particular experiment. And you can see the results of this experiment here. So you'll see that it's running a bunch of trials. Right now, it's actually feeding in dummy metrics because this is just for the demo. So you see that there have been a bunch of trials that have happened, and so you can also look at what is going on in each of the the trials actually. So you see that each trial corresponds to a set of options that is coming from the Bayesian module, and also corresponds to a different CPU request and limit. So this happens for each and every trial that we have here. So this is essentially, this completes, and then you have a recommendation that comes out of it, which will be available as the best trial that you have here. So this is essentially a very quick demo of what we have in Autotune. So the thing that I usually talk about is that I usually compare Bayesian optimization to a Jenny. In this case, you only get one wish. You can invoke the Jenny any number of times, but each time you only get one wish. So now we need to get really creative with the wish, right? So it's something like, I want to be on a beach in Hawaii with my wife and kids and walk into my large house with this great internet connection and so on. So because you just have one wish, and so you want to try and be very careful about what exactly that you want to wish for. So I would like you to keep this in mind as Kusuma takes you through the results that we have obtained so far. So Kusuma, you want to take over?
Yeah, thanks, Dinkar. So far, you have heard the theory. Now let us look into some actual results. So I'll go through the results of the different experiments which we have capturing in the Autotune results repo. Do take a look into the results repo if you want deeper understanding of the results. And if you have any questions or comments about the results, you can always raise an issue in the same repo. So all the experiments we discussed today are run on OpenShift cluster using Tech Empower framework benchmark. The Tech Empower framework benchmark has aggregated benchmarks for all possible frameworks on many languages, including Java, Python, Go, and many more. So for our experiments, we are using the Quarkus REST-EZ benchmark for Java. And for the following results we are sharing, the requests and limits are set to the same. The GC policy has been fixed to the G1 GC and the max RAM percentage to 70. As many of you be aware, the max RAM percentage decides the size of heap in relation to the container memory allocated. Also, we have run all these experiments with the constant float. So there is a list of 31 tunables here, which we are using for our experiments. The CPU and the memory limits are from the container layer, and we have 25 from the hotspot and 4 from the quarkus, which we are using. So in the hotspot layer, you can see there are both the range-based tunables as well as the categorical ones. So you can see for each tunable, what is the default value and what is the range we are using as part of which we are going to feed into the Bayesian optimization. For the range-based tunables, the initial values were chosen doing a cursory study of each tunable. And over the course of experiments we ran, and based on the results we got, we fine-tuned those ranges, which you can see in the later slides. Let's get into the results. So we started our experiments with an objective function to minimize the response time. So this experiment ran for 100 trials, and each trial uses a different configuration generated by Autotune. The zeroth trial is the default configuration where the TechEmpire benchmark is run with no changes to the runtime configuration and no resource requests and limits are set. And for the other trials in this experiment, the upper limit of the CPU is set to 32 and the memory is set to 8 GB. And the other tunables, which we mentioned in the previous slides, it uses the same ranges as mentioned earlier. So in this experiment, you can see that we see a lowest response time at the 59th trial. And also you can see that there is no data in between the trials. That's because, so it means that the configuration failed to come up for those trials. So the failures could be out of memory or it could be anything related to the configuration. And we are using the Optina framework as part of the Bayesian optimization, and it actually works in phases of exploration followed by exploitation. So in this particular experiment, you can see that the first 10 trials is in the exploration mode, where you can see the results vary a lot, and then it actually starts exploiting in the ranges where it thinks it can get better results based on the values of the objective function from the previous trial data. So this process of both exploration and exploitation repeats in the subset of trials for the whole experiment. So for the full results, you can actually look into the experiment 4 in our Autotune results repo, which we have mentioned. So you can see 60% better response time and 19% better throughput in this configuration, but it has come with the cost of higher CPU. So you can see the CPU usage is higher in the Autotune config compared to the default config in that page. So, and for each experiment in our repo, you will find few files where you can get the detailed understanding of our results. So the experiment data.csv is the file where we add all the raw data related to the trials in the experiment. And the benchmark YAML has the configuration used for the benchmark, which includes the list of all the tunables we are using along with the ranges, and then the repos used, and what's the load we are using. So it has all information about how we are running the trial. And the next one is the best result config YAML, which contains the best configuration generated by Autotune in an experiment. So as we have seen in this experiment, we see a higher CPU usage. So it's time we have to tune our wish again. So now this time we became a little smarter, and with this we thought we have to restrict the resources this time. So now instead of using the whole course available like earlier experiment, we are restricting it to use the 4-core 4 GB. And to mention, there is no relation between our previous experiment data and this experiment because we ran it on a different hardware. So, but you can compare the defaults with all the trials in a particular experiment. So this experiment also ran with around 100 trials. The default config in this experiment uses the CPU request and limit set to 4 core and the memory request and limit set to 4 GB. And there is no change in the runtime configuration. And as you can see, the lowest response time in this particular experiment is observed at the 64th trial, which is 1.82 milliseconds, and the default is with a 5.01 milliseconds. And you can actually see the similar behavior of the exploration and exploitation, which we were discussing in the earlier experiment. So you can see the first set of trials it has explored a lot, where you can see all the results are getting varied a lot. And then the next set of results where we are within the same range of the data, and then the exploration and the exploitation. So even with the fixed resources, after we have set the resources to 4-core 4 GB, we still see the better response time, which is 64%, and we do have a 6% better throughput as well. And you can observe from the results repo, which is the experiment 6, the CPU usage is almost similar to the default one with the config. So we have the So with this, we can say the cost is almost similar between the Autotune config and the default config. So can we think like we got everything what we wished for? I can say yes. But did we wish for everything what we wanted? So I could say no. That's because if you look into the data closely, we are seeing a very high tail latencies. So now again, it's time to tune our wish. So this time, the wish is like we want to keep the cost the same and give me the lower response time and high throughput, and also keep our tail latencies lower. So for this, we added a few weightages to the metrics as well. So by giving priority to the response time and then the throughput and the max response time. And again, as I mentioned earlier, there is no relationship between the previous experiment and this experiment, as everything was run on a different hardware. So the 0th trial again here is the default config with CPU and memory requests and limits set to 4 core and 4 GB. And there is no change in the runtime configuration. And in this experiment, we see that the lowest response time is observed at the 97th trial, and where the default, which is around 2.39 milliseconds, and with the default being 14.21 milliseconds. So we did see a better response time, which is around 83% this time, but with 1.3% better throughput, and the latencies are way lower compared to the earlier results. So you can actually look into the repo for detailed information of the results, where you can get the charts for every metric available. And we can say now we finally got everything that we have asked for. But more importantly, we asked for everything we wanted, being cost being almost the similar, and then better response time with a good throughput and the very lower tail latencies. So now we actually calculated the cost of the hardware. So by exploiting the data we got from the previous experiments for both the default and the Autotune configuration. So we did measure how many instances it would take to handle 1 million transactions, and applied it on to a matching AWS configuration, which is an extra large, which has 4 core 8 GB. So we observed with the Autotune config, there is an 8% reduction in cost. So with the Autotune config, it performed better both in the performance metrics as well as the cost. And here is the next slide, please. So here is the best configuration for our take 3 experiment, where we have better response time throughput and the low tail latencies. So you can see that on the right column is the value for each tunable, which we got from the Autotune. And the ranges in the bold are the tuned ranges based on the results of the previous experiments. And interestingly, the Autotune has flipped some of the defaults for the categorical ones, which we showed it in bold, where it gave the best configuration. So this had some conversations in our in-house OpenJDK team, and we have the discussions available in the repo as well. And we welcome your comments on the same in the repo. And as an extension to the previous experiment, we did another one where CPU and memory were kept constant, and only the other 29 tunables were used to optimize. So this experiment mainly highlights the benefit we get by tuning the JVM parameters and the quarkus tunables. So we did observe around 81% better response time again, and where the data is available in the Autotune results repo in the experiment 12. So this time we collected the percentile information along with how many requests were served within a specific time. So this data shows that in the default config, you can see that only the 5% requests were handled within 1 millisecond, and 60% were within the 10 milliseconds. But in the Autotune config, you can see 78% of the requests were handled within 1 millisecond, and 16% in the 10 millisecond range. So this shows that the configuration generated by Autotune, so 95% of the requests were within the 10 milliseconds, whereas with the default, it's only around 65% of the requests. So we are doing multiple experiments, and we do have multiple experiment data available in our repo. You can actually go and look into the results and comment on it. And the other new part which we are doing currently is, as there is a lot of buzz in the community regarding the GC policies and the appropriate resources for that, we are looking into the particular problem and ran some experiments on the same. We do have some initial results in our repo, and you can actually check it out in experiments 13 and 14. Over to you, Dinakar, to take through HPO.
Thank you, Kusuma. So now I just wanted to mention that we are working towards releasing a Autotune MVP shortly. It should come out hopefully by the end of next month. However, we do have something that you can try out right away. So if you remember the Autotune architecture, we had a HPO service that was running here that was providing the configurations. So what we have done is to take that out of Autotune and run it as an independent service. So this is available in the Kruize/HPO repo. So HPO can be run right on your laptop, and it provides a simple REST interface. And we also have a gRPC interface as well to be able to access this service. We also have a couple of demos that are running, that you can run. So it's available here in the Kruize demos repo. So you can see that there is a HPO demo set up here. The one that I showed you earlier was actually this script, Autotune minikube demo setup.sh, and you can run the HPO demo using the HPO demo setup.sh. So actually, the HPO can, and with just the HPO service, because it can run right on your laptop, it'll make it really easy for you to try this out. And it's not tied to Kubernetes in any way. It can be run natively as well as within Minikube as well. So it will make it easier for developers to get their hands on HPO and try it for all kinds of use cases that we can think of. So just a quick word on all the repos that we mentioned today. The project is github.com/Kruize, under which we have all the repos. Autotune is Kruize/Autotune. Demos are available in Kruize-demos. HPO is Kruize/HPO. Results that Kusuma was talking about is in Autotune results repo. And the benchmarks repo is where we have aggregated a few of the benchmarks and basically made them YAML friendly and so on. So it makes it easier for us to run the experiments that we have. And we would love to hear back from you. If you have any comments and questions, you can post them on GitHub directly. You can also join our Slack, as it's mentioned out here, or you can even send us a mail at kruize@redhat.com. So we would love to hear back from you and look forward to collaborate with all of you. Thank you so much.
Wow. Okay. I apologize upfront to any container that I've offended in the past, and I should have actually run this tool set and understood this before I actually size my container. To me, it's how much memory you have, and the classic Java developer, all of it, all of the time. And I'm learning about using code spaces around how you need to have such a fine-tuning understanding of your container, of your Docker container, and your Kubernetes cluster. I need to do a lot of reading again to understand all of the metrics that you put up there. But it's great to actually show that there is a body of information already there that you can actually go in and choose your container and also your size it quite well. Brilliantly done.